often in LTI systems and circuits that you design, it may so happen that it might be easier to compute the response of the circuit for an unit step signal. So why is that? For example, let's take a circuit, something that you've designed. So you have some circuit, arbitrary circuit, which looks something like this, let's say. And you have a switch connected to a voltage source, and let's say this is the output. And when you close the switch, you connect, let's say, a battery, a DC voltage battery connected, and then you observe the output here. Now, what is the input in this case? So the input is basically nothing but the voltage applied across these two terminals here, and that would basically nothing be unit step signal, right? So when you close the switch, what you get, a voltage that is applied instantaneously at that time, and from then on, it's a constant voltage that is applied at the input, which means this can be modeled using a unit step signal. So it's easier to apply this unit step signal than to apply an impulse. So just to apply a spike as the input is very difficult. How will you generate this spike? Like instantaneously, you need to have infinitely large voltage, right? This is very difficult to generate in practice. So often, if you want to find the impulse response of a system in practice, it becomes slightly difficult. So it's easier to find the unit step response. You just feed in this, observe the output, then that is the unit step response. Now, what if you have only the unit step response? How is this useful? Is it actually useful at all? So that's what we'll see here. So the output of an LTI system for its unit step input is called the unit step response. So what essentially are we doing here is nothing but we are first putting an integrator to the impulse. So this unit step can in fact be represented as what? So u of t is nothing but the integral of the Dirac delta signal. Remember, this is what we saw earlier. So you can represent this unit step as the integral of the Dirac delta signal. So when you apply the unit step signal to a system, it is as good as just adding an integrator block in front of it and then feeding the impulse signal to this entire system and observing its output. So what have we done here? Now we have introduced another LTI system in front of the actual system. So this h of t is the LTI system which we wanted to characterize. But what have we done? We have cascaded an integrator in front of this LTI system. But we know that the integrator is also an LTI system. Because the integrator is also an LTI system, you can change the order of the LTI system. Remember, this is what we saw earlier. When you have two LTI systems, and as long as the outputs are stable, you can just change the order. So we have changed the order here, and as you can see here, you can say that the output is now coming from the integrator itself. And these two systems that we have here, this one and this one, are equivalent because both are LTI and the outputs are bounded. As long as the outputs are bounded, you can change the order of the systems that you are cascading as long as each of the individual systems are LTI. We know that the individual systems are LTI. So when the individual systems are LTI, then the order does not matter. So what do we have here? So we have that this system is same as this system, which is nice because just by feeding a unit step as the input, we observe the output, and from that we can actually get back the impulse response. How is that? Now, because this is the output that we observe, we actually want the output at this point. Okay, let us call this as some z of t. This is what the output that we want, but what we got here is the output at this point. So now, if we can differentiate the output that we got, then we would get back the input that was actually present here, which is the impulse response that we wanted. So even if you cannot apply an impulse signal in real life to a system, you can apply the unit step, observe the output, differentiate it, and get the impulse response back. So this is a very nice way of obtaining the impulse response in real life, even though you cannot actually create an impulse signal in real life. So this is how the LTI systems and its properties are useful for us. Okay, so as long as you know the properties, you can use them in some way, in creative ways, to actually help you characterize an LTI system fully. Okay, now let's say I observe this y of t. So that y of t here is the unit step response. From the unit step response itself, without even differentiating it, can we characterize the system properties? Let's say we want to talk about its stability and its causality. Can we talk about these two properties just by looking at the unit step response? It so turns out that it is possible. We can talk about the causality as long as the unit step response has 0 values for, let's say this is some response that we get for a unit step input. As long as it has 0 for all values of time which is negative, then you can say that the system is still causal. That's because it's the same reasoning that we had earlier. How do we reason this? So remember, we know that if the impulse response has non-zero values for the negative value of time, we know the system is non-causal. So we can take the derivative of the step response, and from that we can know what would be the impulse response. So if the step response has non-zero values here for the negative values of time, we take the derivative, that will also have non-zero values, which means the impulse response will also have non-zero values here in the negative values of time, and hence it will be not causal. So to ensure causality, we can say that the step response should be 0 for negative values of time, which is the same condition that we saw for impulse response as well. Similarly, we can say the same thing about stability also. As long as the step response is absolutely integrable, we can say the system is stable, but once again this is a sufficient condition but not necessary, meaning it can so happen that in certain cases that the step response is not absolutely integrable and still the system is stable. So these conditions that we get from the step response are only sufficient but not necessary conditions. This condition need not be satisfied, but still the system could actually be stable because of we taking the derivative here, and then only we can get the impulse response. Okay. So we can still comment about the stability of the system. If the step response is absolutely integrable, then you can say for sure the system is stable. But if the step response is not absolutely integrable, then we cannot say for sure that the system is stable or not. It may be stable, it may be unstable.